Hello, Physics 2. All right, so I'm hoping this is recording because I have had to re-record multiple lectures so far today. All right, so we're going to be continuing on with S3. So we took a little hiatus in the first part of Monday's lecture to just go through some concepts with waves and interference patterns and look at some pretty pictures to give you some visualizations before we get into more of the theory. So we left off talking about interference, destructive interference and constructive interference. So destructive, dark lines, constructive, white lines. All right, so now we're going to be moving on talking about interference maxima and minima. So two cosines can add up add up to give a maximum with 2 times the amplitude and 4 times the intensity. This occurs at path interference (0, lambda, 2 lambda, 3 lambda, and so on and so forth. So at these positions, you can get twice the amplitude and 4 times the position, 4 times the intensity. This is the downside of going immediately from lecturing on Physics 1 into Physics 2, is that I start to confuse my physics terms. Also, 2 cosines can add up to give a minima with 0 amplitude and 0 intensity. And this will occur at lambda over 2, 3 lambda over 2, 5 lambda over 2, etc. Okay, and of course you can always prove these to yourself. All right, so building on this, predicting radiation patterns. So this is all about interfering waves. So once we understand phase, so in phase and out of phase waves, we can move in the direction of predicting bright spots and dark spots. And this is all related to, we need to know the path difference. Between 2 wavelengths. All right, so let's say we had, let me draw a setup and then I will talk about it. So we have a source A, a source B, a point C that is very far away, where we are making observations. This should be made even bigger. Okay, so we've got two sources of electromagnetic waves. So EM wave sources here and here, and we are observing them at point C. Let me drop in some perpendiculars so we can talk about a couple things. So this is a right angle. And we can drop in a perpendicular right here. And so we've got theta, theta, delta L is equal to d sine theta. All right, so with C being very far away, we can say that AC is approximately the same as BC. C is far away. And A and B are actually quite close to each other. This only works if C is far away. So therefore, using this, the path from source 1 to C is approximately delta L is equal to d sine theta, longer one, two, A is there. Oh my goodness. This is a problem with having to read your own writing. Okay, so quick update, AB source 1, 2. All right, so, and you've got d sine theta here. D sine theta longer than the path to source 2. So the path difference delta L is equal to d sine theta. If delta L is an integer number of wavelengths, there is a maxima at angle theta. If delta L is lambda over 2, 3 lambda over 2, 5 lambda over 2, there will be a minima. At angle theta. And the interference pattern is directly related to the spacing of these two sources. So depending on if you're looking to observe something particular at position C, then you need to think very carefully about how you've positioned it. So I used a Mach-Zehnder interferometer to analyze the density of different gas jets, and I had to align my laser perfectly with very precise differences so that I could learn something about the density. And this was all related to making sure that I knew exactly where the sources of my electromagnetic radiation were coming from. And I used exactly this formula in doing this type of analysis. And I worked with a little bit of tomographic code to go after this. So this has very real applications even today in lab settings, even though this isn't exactly a new concept. Okay, so moving on with this idea. So same idea. So if D is less than lambda, you will only get constructive. Get constructive interference. Interference at theta equals 0 degrees or theta equals 180 degrees. So that's for d sine theta less than lambda, which is this case. If d less than lambda over 2, you can never have zero intensity. And on your own, prove this. Not optional. Okay, so now let's look at two-source interference. So, maxima intensity so this would be 4 times the original intensity I naught. Delta L is equal to d sine theta. So this would be at 0, lambda, 2 lambda, 3 lambda, etc. So I'm just kind of compiling ideas together. Minimum intensity, which is 0, occurs at delta L is equal to d sine theta is lambda over 2, 3 lambda over 2, 5 lambda over 2, etc. And no zero intensity if d is less than lambda over 2. All right, so that sort of summarizes our two-source interference pattern options in terms of constructive and destructive interference. So now we can move on to two-slit interference. That famous experiment, so you did see it in the PowerPoint slides that I lectured over. So you have seen this in slides. And now we're going to move towards doing some calculations. Okay, so essentially what you've got in a double slit experiment is you've got your coherent light source, typically a coherent light source, and you're going to shine it through two slits, which we see here. By the way, they are still doing double slit experiments. A friend of mine, when he was in grad school, he did a double slit experiment, and they were able to do a reanalysis of different states of light and further improve on our understanding of quantum mechanics. Very cool stuff. But there'll be some distance d here, which is the spacing between the two slits. You've got your coherent light source. I have way exaggerated this. And you're going to get this kind of cone. And so you'll have an angle theta here, some length L, and then some spacing X. So, and this would be a screen or photodiode or some sort of detector, maybe a CCD camera, I don't know. And you'll have your light. So let's see. I did not draw this very well. Okay, so okay. What I wanted to draw is a maxima to maxima. I drew too many wavelengths. All right, so let me try this again. Maybe this time I will draw that first and then work backwards. So that's still the screen or the photodiode, and we're going from a maxima to a maxima all the way back to the slits and the source. This is why I don't grade you guys based on your drawings. This is why, because I would be a giant hypocrite. Okay, so looking at maxima to maxima. So L for this particular setup is 2 meters. D, which is right here, is equal to 0.5 millimeters, so half a millimeter. And the distance from maxima to maxima is 2.4 millimeters. Okay. So we can use this particular setup to calculate the wavelength of the laser light. So we have the length between the detection and the source. We've got the angle theta. We don't have the angle theta. We have the distance from maxima to maxima, and we've got the distance of the slit. Okay. So at the second maxima, d sine theta equals lambda. So therefore, sine theta equals lambda over d. And for small angles, sine theta is approximately tan theta is approximately theta. So lambda over d is approximately x over L. This sucks. Okay. Either one. Therefore, lambda is equal to x over d over L is equal to 2.4 times 10 to the minus 3 meters. We want to get everything into the same units. 0.5 times 10 to the minus 3 meters divided by 2 meters. And you get that lambda is equal to 6 times 10 to the minus 7 meters, which is equal to 600 nanometers of light, which is red light. And so that is the type of information you can use from or learn from the double slit experiment. Oh my goodness gracious sakes alive! From the double slit problems. You know, I'm not going to do multiple takes of lectures for very, very obvious reasons. But you know, if you missed me stumbling over my words, I mean, at least I, can give you what you want in that case. All right, so building on this, we can now talk about diffraction, which is otherwise known as multi-source interference. So interference. So this is patterns from a few wave sources. And diffraction, patterns from lots of sources. Okay, so what we're going to do to introduce diffraction is we're going to start with thinking about X-ray diffraction because there's some really useful applications for this. So, and you'll see why in a second. And they do have X-ray lasers, which we use to do X-ray diffraction. You have to take a pretty intensive radiation class in order to use them. I've taken that class. If you get dosed, you're looking at some serious X-ray burns. And I've seen the gory pictures. And what's really tricky about X-ray lasers is you cannot see them. So you have to use all sorts of tools to know exactly where they are. But yeah, you will not see them glinting off anything. So typically in a very clean laser lab, you will not see the beam because you can only see the beam when it's reflecting off of something else. So I worked in a very clean laser lab and you could only see the beam like with paper to align it. So if you ever look into a laser setup and you can see the beam, that means you're actually in a dirty laser environment. Fun fact. All right, so we're going to focus on X-ray diffraction, which is at a particular wavelength. And the reason for this is the X-ray wavelength is approximately the diameter of an atom, so where d is the diameter of an atom. So we use X-ray diffraction to learn about materials. So if you recall Physics 1, when radiation hits an array of atoms, they excite, and electrons accelerate, and now we know that an accelerating electron causes re-radiation. Okay. High intensity re-radiation, so remember we now know where you get high intensity radiation from. You're looking for very constructive interference. So high intensity re-radiation occurs in directions with path differences of adjacent atoms lambda, 2 lambda, 3 lambda, etc. So remember, the X-ray band is wide, it's tunable. All right, so I'm going to draw some pictures and get some paper. Let's consider an X-ray beam, which would be a laser beam that hits a crystal lattice. And we're going to assume it's just a simple cubic lattice. Okay, so you've got your crystals, and you've got your incoming laser beam here. And another incoming beam here. And then you've got these different sides there. So this is just a simple reflection. And so we can use the law of reflections to go after it. Okay, so we don't really have any interference in this particular case with just this one row of crystal lattice that we're looking at. Okay, so to go after interference, so we are going to bring in interference. We need to go a little bit deeper into the crystal. So the first layer of atoms will look like our picture. The next layer gets interesting. Well, more interesting. Okay, so, and just remember or recall, re-radiation need not be in phase. Okay, so now we're going to look at what's going to happen if you've got, now we're 2 layers deep into our lattice. So we have, coming in, coming out, call this 2, and then coming in, coming out, we'll call this 1. And so now we've got some d sine theta going on. Theta. I'm going to refer you to your book for a better picture of this. I'm not doing a great job of writing or of trying to reproduce this myself. So there is a difference of 2d sine theta from the bottom to the top. We get this 2 from because it needs to go down 1 extra layer and then it will go up on the other side. So that's more than just d, it's 2d sine theta. So if d sine theta is not equal to n lambda, where n is equal to 1, 2, 3, etc., then the top layers will not re-radiate in phase. And intense reflection or constructive interference occurs when 2d sine theta is equal to n lambda. And we use this so we use X-ray diffraction to determine d in layers of crystals. So if you study crystallography, much of what we know about crystallography nowadays has come from the applications of X-ray diffraction. Okay, so we can do an example. We have a lattice of a crystal, has spacing 4.5 times 10 to the minus 10 meters, and X-ray laser has wavelength 1.32 times 10 to the minus 10 meters, is directed at the crystal. What theta could you have and interference maxima? Okay, so we want 2d sine theta is equal to n theta, and we're just going to look for where n equals 1. That seems easier. Okay, so theta is equal to arc sine lambda over 2d is equal to arc sine 1.32 times 10 to the minus 10 meters divided by 2 times 4.5 times 10 to the minus 10 meters. Theta is equal to 8.43 degrees. All right, so you can see now how these games are played with understanding crystal properties using X-ray diffraction. Now let's think about what this implies about visible light when we're looking at crystals. So if you recall, visible light, lambda is much, much larger than 10 to the minus 10, between 400 and 800 nanometers. And when visible light hits a material, it does not accelerate. E minus. Oh, oops. It does accelerate our electrons, and there is re-radiation. But no X-ray diffraction. So we can't get some really great super constructive interference. So no 2d sine theta is equal to n lambda. And basically from there, the difference in path lengths for re-radiation is negligible. And adjacent layers are in phase. We only see one high intensity. Maximum. So we can learn about some crystal properties using visible light, but it doesn't offer us the same types of learning opportunities as X-ray diffraction. All right, I will stop here.